All right, welcome to the hottest seminar. And today we're very happy to have Greta Coraglia, who's going to speak on the fibration of algebras.
Yeah, thank you, Emily, and thanks for the organizer for having me here. It's truly an honor to be on such a long-running seminar. I hope you don't mind. So I brought some work that it has been quite complicated, kind of mathematically and also personally, historically. And yeah, as you can see, there are many people that contributed to this. Hopefully more in the future. And yes, so I hope you don't mind. I'm gonna just try to tell you how these all started and where we're at and where we want to go next. And at the end, I'll be very appreciative if somebody has something to say or to suggest or to just comment. Okay. So the title of this talk is called the fibration of algebras, and is actually the product of what originally was one question. I don't think maybe with the button you don't see what's happening up there, so I'll try to move these around so you can see. Yeah. So the question that started all of this is a question by Fosco Loregian. He came to me and a few other people in the spring of 2022, and he came with an observation about simple types that he found in Jakob's book. So the I'm going to be moving this around quite a lot. I hope not. That is not so bothersome. Yes.
We don't see the little window. It's okay.
Okay. So it's just my problem. Perfect. Thanks. Yeah. Okay. So he got this example from Jakob's book, and the example was this. So if you take a Cartesian category, then you can then you can build a category ST that has objects, pairs IX, which are objects in C, and homomorphisms, these pairs of maps, where the first map is the map between the first components, and the second F is a map from J times Y to X. So it's kind of a mixed map. And this category was actually introduced to model simple types, as that is kind of the modeling types is the purpose of the book. But then already in the book, Jacobs noticed something that is quite interesting. So out of a Cartesian category, you can build this SC, and in particular, if you forget the second component, that the functor that you get is actually a Grothendieck fibration. I'm going to be saying a Grothendieck fibration just a couple of times, and then I'm going to go straight to say fibration. I know that means many things to people here, so I hope that you remember every time I say Grothendieck fibration, well, sorry, every time I say fibration, just mean a Grothendieck one. Yes, so a Grothendieck fibration and the fiber at each I, which are represent the context, he calls the simple slice. I'm going to be going back and forth between Grothendieck fibrations and pseudo-functors and indexed categories. So let me just recall the basic result that we're going to use, and everything else is kind of the through there. So recall that there is a two equivalence between fibrations over base C and pseudo-functors from the opposite of C into cat. So on one side, it's quite intuitive, I think. So if you start from a fibration, you can think of as just a functor who has a notion of substitution in a sense. So if you go from fibration to pseudo-functor, you just take at each I the category that is the fiber. So in this case, the simple slice. Well, if you go the other way around, so you have a pseudo-functor, then you can kind of collect together all the fibers using this construction usually called the Grothendieck construction. So going from pseudo-functors to fibration, we kind of collect together all the fibers. And this is the part that we're really interested in. Grothendieck, Jacobs noticed that this is actually the simple part of the category SC is fibered over C. But not only that, he noticed something different. He noticed that the simple slice, so the fiber at a given I, is also the co-Kleisli category of a certain comonad, in particular the co-reader comonad, which is the one that takes, given an object I, it maps an object X to its product with Y. So maybe not a super interesting comonad, but still. So there's these things happening. So there is a fibration and there is a comonad. And in a sense, the simple fibration is the result of pasting together all co-algebras for a comonad that is in particular parametric, because at each I, of course, you have a different one, and they are related in a functorial sense that you can imagine. Okay, so in Jacobs there is this observation, but it's not very much developed. So Fosco came and asked a bunch of us, he asked, is this a thing? So is this something that is common in math? Is this something that is interesting in math? Can we find something about this? Because it feels like a very general process. And so this is kind of what I hope to discuss with you today. So today's plan is gonna be, first of all, look for this behavior elsewhere. And actually, we will see that this happens quite a lot. So we will see that it appears in many different places. The second thing that we'll do is we'll try to give a general theory of this, as we often do in math. So we see something funny and we try to give a theory of that. And we'll see that semi-direct product come into play, kind of maybe unexpectedly. Then I'll try to convince you that there is some benefit in trying to write a general theory for all of this. And finally, I'll try to point to some applications that we have been working through, and some that are already concluded and some that I still want to explore. Okay, so first part. So of course, we can look for example of this behavior almost everywhere in math and in computer science. So let me just fix some names. So we denote a category of parameters, and we call a functor f from a times x to x a parametric endofunctor. And sometimes we're going to be asking, we will ask that it is a pointed endofunctor. Sometimes we will ask it's also a monad or a comonad, but we'll come to that when the time comes. Okay, so we denote a category of parameters, and of course, in the case when the parameters are equal to the category that one is taking endofunctors on, so as in the case of the co-reader comonad, or in the case of its kind of join the reader monad. So we have some examples where the two are equal and they're still interesting. If we combine the two, what we get is what is called the state monad. And of course, there is a monoidal version of each of these ones. So for example, if you have enough structure, you can define what is usually called the writer monad, and there's an analog of the other ones as well. While instead, if you have coproducts, you have for example, what is called the exception monad. So all of these make sense, that it's quite easy to imagine how they're built from basic categorical constructions. But one thing I want to point out is that not only are these objects quite reasonable, but it's also both worth checking what happens to their, in the case, for example, of the comonad, what happens both to the co-Kleisli and the co-Eilenberg-Moore construction. So for example, as we said, in the case of the co-Kleisli, that is the simple slice over A, but for the co-Eilenberg-Moore, that is precisely the slice over A. So not only these are quite common and quite pervasive in math, but it's also both worth looking at both their algebras and their free algebras. And talking about algebras, I just want to take a second to give you kind of concentrate with you on a few examples that are precisely taken from automata theory, because of course there's a long story, a long history of algebras and co-algebras and their study, and they're particularly relevant in the context of automata. So for example, as I said, in the case of the co-reader co-monad, its co-algebras are streams. I'm just going to focus on sets for the moment. Of course, we can combine differently the structure of sets. So for example, we can describe a co-algebra, sorry, a co-monad whose co-algebra is deterministic automata. And then we can also make partial automata, of course, just adding a non-terminating kind of marker. We can also describe non-deterministic automata, just taking the parts of the set. And if we want to make things a bit harder for ourselves, then we can describe what are called the Mealy automata and Moore automata. And I'm just mentioning this because we do actually have an application of the theory that I'm about to show you and concerns Mealy and Moore automata. But of course, there's many more examples coming from the theory of coalgebras that might be of interest. Okay. But the cases that I discussed up to this point were cases where the category of parameters was equal to the category of where the endofunctor insists on. And that is actually not always the case, and not always a case where there are many interesting cases where that does not happen. So of course, one of the first that might come to mind to people here is polynomials. So if we fix a locally Cartesian closed category, we can define a certain category of polynomials such that it is a good category of parameters for an endofunctor from the slice over the variables into the slice over the variables that the polynomial insists on. So of course, probably all of you know how that's defined, but this is actually another instance of a parametric endofunctor. And in this case, you can see that A and X are not the same category. And one last example that I want to show you, but it's actually looks very trivial, but it's actually quite deep in a sense that I hope to show in a second, is that of kind of hidden into so it's the curring of the identity in the endofunctor. So if you take as parameters the category of endofunctors of X, then you can define, of course, the functor that at each F acts precisely at F as F does. Okay, so these are a few examples. You can see, probably you can imagine some more on your own, depending on your area of interest. But this is quite a common phenomenon. And if you maybe try to look into this stuff, you maybe have encountered the theory of graded monads or the theory of parametrized monads, as in the works that I put here. And the question, begs the question, is this the theory of graded monads all over again? And the answer is yes and no. So I hope to explain both the yes and the no in a while, but if you have those in mind, it's good that you keep them in mind because they're of course relevant to the discussion. Okay, so now we try to give a general theory of this phenomenon. So we get back to the example that Fosco came to us with. So again, we have a category and we have this category indexing some comonad. We take the co-Kleisli, we paste them all together, and we find the fibration. So there is actually two, if you look at this process, there's actually two things happening all at once. So the first thing that's happening is that out of a category of parameters, you compute endofunctors. And this is the first step. So out of parameters, you get endofunctors. And the second is, out of an endofunctor, you compute its algebras. And I know that here we have co-free algebras, but it's going to be easier if we start with simple endofunctor and algebras, and then we get to the case. So 2 steps. The first step we've discussed quite a lot. Out of a parameter, get endofunctors. The second step, out of a functor, we want to get its category of algebras. These we can always do, and you'll see that whenever we have a natural transformation alpha from G to F, then we get what this is usually called a reindexing functor from the algebras of F to the algebras of G. And this is quite easily described, just a precomposition with the X kind of component of the natural transformation. Okay, so parameters get endofunctors, endofunctors get algebras. Perfect. Now we try to combine the two together, because if you remember, the process of the example from Jacobs was actually combining the two. So parameters get endofunctors, and then endofunctors get algebras. So of course, we recall the Grothendieck's equivalence. So out of a pseudo-functor, we get a fibration U. This is actually not a pseudo-functor, it's precisely a functor. So what we get is a so-called split fibration. And we call these the universal fibration of endofunctor algebras. Of course, when category theory sees 2 arrows directed this way, there's only one thing you can do, and that's precisely computing its pullback. So what this pullback does, it is basically what this is going to be the object that we will be studying. So this PF induced by F, and with this universal U here. And we call fibrations obtained this way fibration of endofunctor algebras. I know it's not very creative and quite long, but if you have better suggestions for this, I think everybody will be very appreciative. Okay, so 2 simple ingredients. Let's see what we can cook from it. Yes, so of course, let me just first describe what are objects in the total category, but I think it's quite evident now. So it's going to be triples, A, X, little x, with A, an object, and X, an algebra for the eighth endofunctor described by F. And morphisms are going to be a bit, well, not a bit more complicated. They're going to be exactly what you think they are, right? So we say that there is a map UF whenever there is a square like this that commutes. Now, what I'll be showing you today is that the fibrational aspect of all of this is actually quite relevant and also quite useful to look at. And in particular, let me just show you just one little hint of the structure that is happening all together when one defines a fibration. So of course, each triple lives over its parameter. And in particular, whenever one has a Grothendieck fibration, it inherits a factorization system. Is called a vertical Cartesian factorization system. And in this case, what this does is actually quite simple. So I try to use the same color to show the relation, but in some sense, first you just do nothing on the parameters and you apply simply F. So you can think of these as this square here on the left. And the Cartesian part is precisely the action of a U. So FUX. And the action of the U is precisely the action of the pseudo-functor. So it makes sense that Cartesian maps are these ones. Okay, so we have these fibrations, and now we know what their objects are and how they behave. And of course, as I promised, and as you can imagine, there's many variants that you can kind of think of this. So for example, if you restrict yourself not to all endofunctors, but only to endofunctors that are monads, then you can both compute algebras. It's Eilenberg-Moore category and it's Kleisli category, and they will in turn give rise to 2 different universal maps of this kind. And each time you can pull back, and we denote these EM and KL for obvious reasons. And also, of course, you can do everything for co-algebras, and you repeat the process with co-monads and such. One thing that we found that it is maybe obvious, but I think quite interesting is the variance of all of this. So in particular, as I said, when you compute algebras, you get a pseudo-functor, so you get a fibration, and the same goes for algebras for a monad. But when you try to get to free algebras or Kleisli, for the Kleisli category of a given monad, what you get is actually has the opposite variance, so you get an off fibration. And when you dualize the whole thing, then basically you get an off fibration, and off fibration. So if we think back to the original question that these all started from, what you get is that we are Fosco's question was actually living in this quadrant of the map that we're trying to draw. So in particular, we had the simple, well, the co-reader co-monad here, and we compute the co-Kleisli, and here is what we get here on the left would have been the simple fibration. So it's good that it turns out kind of coherent to where we started from. Okay, so of course, one thing that people, well, we wanted to do, since we would love to be able to compare the Kleisli and the Eilenberg-Moore construction, but as I told you, the problem is that they have different variants. So we wish we had a fibration morphism going from one to the other, but we cannot do so. So we have some morphisms we cannot define, but some we can. So for example, it's quite trivial to see that if you start from endofunctors and restrict yourself to pointed endofunctors and then to monads, then each of these is a sub-fibration of the one before that. And of course, these inclusions cannot be full because you need to have ask some compatibility of these. Okay. So before we move on, I want to try to justify to you why we use this semi-direct product notation, because it's quite here there's none, but it's quite okay. I'll get back to that at some point. Yeah. Because it was quite a useful observation, at least for us in understanding what happens using the semi-direct product analogy, which is actually a bit more than an analogy. So let me just recall the definition of a semi-direct product of two groups. So for groups H and N, and group homomorphism phi from H to the automorphisms N, you can actually define the semi-direct product of H with N via phi, which is basically has the underlying set, the Cartesian product of the underlying sets, units, the pairs of units, but as a composition, it has in the first component just the H multiplication, and the second component it actually uses, of course, the phi to describe how N and N prime should be related. And this is quite, it's not so far from what happens in our case. So instead of two groups, now we take two categories, A and X, and we take a functor from A to the endofunctors of X. Maybe it would have been smoother if I just wrote end of X, but still. And then when we define the total category of the fibration of algebras, its object, as we said, is actually pairs or triples, but the composition it's what is interesting. So again, in the first component, this composition is defined trivially in a sense. While in the second component, the action of F is key in defining how the two interact. And this is not only a suggestion, but from this we can also kind of derive some intuition a bit deeper. So for example, for a given group G, you can define the holomorph of a group as the semi-direct product of automorphisms in G with G. And the two, of course, when the two are related by the identity. But this relation I've already shown you, because this is precisely what happens, like in our notation, this is precisely the total category of the fibration of algebras induced by the identity. So you see that in a sense, our total category is kind of an analog of the holomorph of a group, in a sense. So yes, so this notation we found quite useful. So except for notation and a bunch of definition, there's also a few results that we have proved. So the first thing that we try to do is that, of course, the most interesting case is that of Eilenberg-Moore algebras, or algebras for a monad. And so the first thing that we tried to do was to characterize fibrations of Eilenberg-Moore algebras, and we showed that a given fibration is a fibration of Eilenberg-Moore algebras, meaning it fits in a pullback of the kind that I have been showing you, if and only if there exists a morphism of fibration which is monadic as a one cell in fib over A. And this in turn, maybe to make it more intelligible, this is equivalent to having a fibered H and a fiber left adjoint to it, such that the Eilenberg-Moore object in the fibrations is actually equivalent to B. So we can characterize, in a sense, things that are fibrations of algebras whenever we have a given A and a given X. Just look for monadic one cells in the fibration of algebras over A. And then, of course, in the simpler case, so in the case that we started from, we defined, it's easy to see what this H should do. So remember, here we have a parameter A, a big X, and a little an algebra in its carrier. And so in this direction, you just take the parameter and the carrier, and the other way around, you fix the A and take the free algebra over the object that you're considering. So this adjunction is precisely the adjunction that kind of free-forgetful adjunction. Okay, now I hope that you kind of got accustomed a bit to the notation and to the question that we might be asking. But I want to try to show you some benefits that one might get when working with this kind of stuff. Because, okay, sometimes we do math because it's pretty and that's okay. But the main point of doing something so general is that we can probably hope to address many problems all at once. So let me just show you what kind of problems we can discuss. So, of course, when one deals with growth-index fibration, the main character is the reindexing functor, right? The thing that allows me to go from algebras for F to algebras for G. And when one works with fibrations and one is looking at reindexing, one of the questions that is usually asked, some of the questions actually involve asking whether there are adjoints to this reindexing. And these have a very nice logical interpretation, but they're also quite interesting in themselves. And in particular, they're quite interesting when one tries to look at limits or co-limits in the fibers. Well, why? Because, for example, if one were to prove that a certain right adjoint exists, then one could follow the right adjoint and transport the limits along each reindexing, for example. So these three problems kind of are all related, but we can use them to address bigger problems. So for example, we can use them to address problem of completeness or co-completeness of the total category. So we have a few scattered results with this respect. I'm going to show you just three, actually two more than what you've seen right now. We have more, but I wanted to show you just three that kind of give me an idea of the possibilities. And of course, to go back to the question, is this not just the theory of graded monads? Well, no, because we heavily use the fibrational structure to prove things about this category, and we could not have done that without that perspective, I think. So the first thing that I've already told you, actually, it follows from theorem 0, which was the one characterizing this kind of fibrations. So in particular, if we have a parametric monad, the forgetful functor is monadic. This is what I just showed you, the free forgetful fiber, the junction. But from these we can derive that it creates limits. So this tells us something, whether we know something of A and X we can use to derive stuff about the total category of the fibration of algebras. Another result that we have is that if we have a parametric monad such that it preserves filtered colimits separately in each parameter, then if X is co-complete, then so is the total category. Now I forget okay, it's okay. So we can deduce co-completeness from local behaviors of F and X. And one last thing that I just want to mention, because I want to use it later, is that if X, so if a category X is K accessible and F is only restricted to K accessible functors, then each reindexing has a left adjoint. So in particular, it means that the fibration, this is equivalent actually to saying that the fibration of algebras is a bifibration. So it means that it's both a fibration and an off fibration. Okay, so I know these are many results, and if you scatter, then it's kind of random, but just to show you that these are some questions that you can ask and hopefully answer with this perspective. Okay, so now to applications. And yes, so the first applications, well, the first application that came to mind, but is actually not quite developed yet. So I hope we have the time to discuss some about this today. So remember, we defined polynomials. So for a given diagram such as this, we can define an endofunctor from the slice into itself. And there is a famous paper by Moore and Palmgren that showed that if a locally Cartesian closed category has W types, then so do all of its slices. And of course, by W types in this case, from the semantics of this, we mean that they're initial algebras for a particular polynomial that is the one where the variables are just the terminal object. So they show that if a locally Cartesian closed category has W type, then it does for each slice. And the proof at the time was quite complicated and it took some time, but then somebody else came, particularly Nicola Gambino and Martin Eilenberg, and then in 2009 they gave kind of a simpler proof of this, because they show that there is an adjoint pair, and this adjoint pair lifts to some algebras, and since they have left adjoints, they must preserve initial objects, and in particular, then this is all done in one swoop. So the proof is very nice, but if you know this proof, then and you know everything I've told you now, you might be wondering whether this is a bifibration-like property. So can we frame all of this now in some functor being a bifibration? So what is the plan that we have in mind? But as I repeated, just not concluded yet, but hopefully we'll get there. So let me just describe the strategy for the moment. So by our theorem number 3, we have that the fibration of algebras for omega accessible endofunctors from set I to set I is a bifibration. This we have from our theory. But then, in particular, polynomials are omega accessible, so we can pull back and get our kind of fibration of algebras that we've been studying. So you see that here you have pairs of a polynomial and algebras for an endofunctor for the endofunctors induced by the polynomial. And so we have a bifibration, and these we can conclude it's a bifibration, but more than that, there is a nice result by Young Kim Kok in his notes. Here I wrote 2020, 12, okay, whatever. Yes, it's 2016, the last edition. But yes, so in particular there, he shows that polynomials are themselves fibered over sets. So bifibered over sets. So you see where I'm getting at now, hopefully. So he defines a particular category with certain morphisms that are mediated by these kind of squares. And it makes sense that polynomials are fibered over sets, because what you basically do, you just forget everything but the endpoints. And so our hope is that if we can get from this bifibration to a new bifibration that kind of considers all i's at once, then we can compare, we can just attach one to the other. So we will have this bifibration from Koch and this bifibration of our theory, and then the result will be concluded all at once, because the left adjoints will be the kind of left adjoints that they use in the Gambino and Island use in their proof. And I think it also would be nice from a kind of intuitive perspective, because if you know a bit about, if you think about algebras for polynomials, it makes sense that they are twicely fibered in a sense, because you have the level of the endpoint, and you have the level of the polynomials, and then you have the level of the algebras for the polynomial and the functor induced. But yes, as I said, this is not concluded, so this is the plan, but we have kind of a couple of problems. So of course, if you look at these, there might be some variance issues, but that we can correct, because being a bifibration, if you were to switch everything up, so a fibration would be an op fibration, and an op fibration would be a fibration, but the result would be the same. So that will hopefully not be a problem. But the other question is that if that is two-dimensional in a sense, because we're trying to consider too many things all at once, so maybe we'll need two fibrations of some kind. But yes, so this is kind of, again, some form of problems that we can address in this context. Another application that we're thinking about is that to deparametricity in particular. So if we consider two functors, L from A times X to Y, and R from A op times Y to X, such that they are kind of locally adjoint, and naturally in all the things that you might think of. Well, these is objects like these, which are quite common, are actually what led Hatke to introduce deparametric monad in particular. So he gave this definition, which I find reasonable, but quite complicated to work with. So he said that a deparametric monad is a functor from A op times A to endofunctors, such that when A is regarded as a free XX enriched category and T as a profunctor, then T is a monad in the category of profunctor. So heavily using strict formalism, but so these objects, this T object here kind of looks like the ones that we've been dealing with, just in the case where the category of parameters is kind of mixed variance in a sense. And yeah, okay, I won't tell you about the monad laws, but the interesting thing it does is that it also defines a category of deparametric 3 algebras. And these category as objects pairs, kind of such as in our case, and its morphisms are precisely those that kind of look like a Kleisli, right? So we have a morphism from AX to A prime X prime is a morphism in X that is from X to T A prime X prime. So there is kind of a need for things that are deparametric, and this is one answer that has been given to that. But we want to try to put now what we have and compare it with Hatke's theory. So we can define, now assume we have these t out of a, yeah, now I wrote it like a subscript, but just think of LA blank blank, of course. So if we define a functor mapping A prime A to the endofunctor RA prime, so we can show that this is a functor, we can show that it's actually functorial. The moment we compute kind of the category, the fibration of algebras construction, we can show that what comes out of this is actually comparable, not only that, but there is a kind of like comparison functor from our algebras to their algebras. So this is, in a sense, is kind of another way to attack the problem. And I'm almost done, really. I just want to conclude with a list of other things that we have been working on or are currently working on. So as I told you, there's quite a few results that one can formulate with respect to completeness and incompleteness. And in particular, in this paper, people use this theory to show completeness for categories of Mealy and of Moore automata. So there's something that can be done in other categories of automata, hopefully. One thing that I've been thinking about, but I have not developed yet, but I think it could be interesting if you know a bit about the treatment of structural induction and co-induction by Reimaa and Jacobs. I think these techniques would be quite cool to compare with that. And finally, there's quite a lot of algebra happening here, even if it, well, okay, maybe everything is called algebra of something, so it's quite understandable, but there's a lot of formal algebra happening. And in particular, we noticed something at some point. So if you assume that the category of parameters as initial objects and the category of the endofunctor insists on as terminal object, then you can induce two adjunctions. So of course, the one going outwards are the forgetfuls. And in a sense, the left adjoint to these forgetful is the one that takes the free algebra at the initial object, and at the initial parameter, excuse me. And the other way around does kind of the dual of that. And not only that, but these two adjunctions compose into what some people call a zero sequence. So basically composed to constant zero, well, constant initial, constant terminal. So there is some theory about these things. They're kind of can be thought of as a generalization of, in a sense, of some exact sequences. So there is some things of algebraic interest that one can derive from this. For example, there's the theory of torsion theories appears to be quite relevant, but I'm afraid it's not my forte. So I just thought to mention it because maybe some people are interested in that kind of algebra, and there's something to be done here. Okay, so just to conclude, as I mentioned, this is, I hope it's okay that I brought some work that is still in progress. And in particular, I have some questions for you as well. I hope it's not bad, but since all of this feels very algebraic in nature, I'm wondering whether it could be useful also to, well, of course it's useful to formalize it in hot. But since I'm not very good at formalizing stuff yet, I'm wondering if you see any obstacles, like obvious obstacles to doing that, those that have a bit more experience with the topic. And the second question for you is that whether you have any problems that you might be interested in throwing this kind of technology at. And yes, just to say a couple of more words. As you see, this is kind of a quite a confused project because we have many examples. We have many results. Maybe not all of them are interesting. I don't know. But the point is that there's so many directions that we can go, and as all researchers know, when there's too many directions to go, then it means there's no direction to go. So we're a bit lost. So yes, thank you for listening, and yeah, I'm ready for questions.
Great. We traditionally offer silent applause, so. Fantastic. Who wants to start the questions?
I'm taking my notebook. Oh,
Yeah,
sorry.
please go ahead.
I mean, can I just say something, or do you want to ask a question?
Well, I was going to, but why don't you go first? So,
Okay.
no.
Yes, I was telling Dan, as this is a kind of a long and complicated story. So I'm really glad this is gonna be on YouTube, because actually this project would have stopped at page maybe 6 if somebody had not given a talk, and that talk was put on YouTube and somebody watched that video and contacted us. And so if you don't feel like talking or I don't know, even saying random stuff now, please contact us, because we're quite lost, as I said. Please.
Great. So I was curious about understanding these bifibrations involving polynomial functors a little bit better. And I was wondering if you could tell me, I mean, maybe this was on the slide and I just missed it, sort of what the fibers are for either yours or Joachim's.
Yeah. Okay, I can tell you what the fibers are up to this point, of course, because I'm not here yet, but I can kind of guess. Okay, so actually, this is not the bifibration that Joachim has, because as you probably know, there's many notions for polynomials, and there are many notions of morphisms of polynomials. I chose this one because it's a bifibration, and because it actually kind of fits with our format as well. So there's hope there. So this one, in particular, you see the square, because I think the notation is for these kind of morphisms. And the bifibrational part, so an object here is simply a polynomial, so the triple of maps of this kind, and they are sent to their endpoint. I put this triangle here, and this is not the bifibration that he introduces, because in his case, he also has like admits different endpoints. So you can start from a J and end with a J prime, and it's not a problem. But in our case, since we're dealing with endofunctor, I just focus on those that have identical endpoints. But if you have some problems and you need to use 2 endpoints, it works as well with 2, and you just project to the pair, and it's fine. Ours up here instead, here you have polynomials on a given I, and in this case, the morphisms here are precisely those that you get having for you the identity. So it seems like they might be compatible. So here you have a triple, there's a polynomial, and here you have f, and then you have an algebra and its carrier for the functor induced by f. So they seem compatible, but I'm a bit concerned going from the left to the right of this arrow, because I can't really tell whether we should go 1 dimension up or just add another layer of fiberedness in a sense. So 1 level up would be that instead of a pseudo functor, you get a functor that goes, instead of cut, it goes into functors. So this is what I mean by one level up. So maybe that is not a 2 fibration. But yes, but we need to check a couple of things, because we want the left adjoints that are implied by these to be precisely the left adjoints that come from the proof in Gambino and Island's paper. And I know that this seems like one of those things where you try to solve a problem that's been solved in a simple way. You say, no, this is simpler, but then it takes 20 pages to get to the simpler. So maybe it's not really simpler. But I think it's quite neat to, if we really were to do it, to look at at polynomials as a layered kind of process, because it actually is. I mean, I feel it like it is.
Great, thank you.
I have a question.
Please.
So I'm currently trying to understand a paper called Fibrational Initial Algebra, Final Co-Algebra Coincidence. So that's why I was attracted to this talk. Do you know of any of this, anything that you've looked into? You've looked at like this coincidence of initial algebras, carriers of initial algebras and final co-algebras?
I remember reading something, but I can't recover in my mind precisely what that was. So if you can repeat, yes, I'll be gladly listen. Like, or say something more about that. So the word is coincidence.
Yes, so the paper is fibrational initial algebra, final co-algebra coincidence over initial algebras.
Yes. So that was like they do an iterated process, right?
Yes, they have like some sort of chain construction. But do you know if this relates at all to that paper? Or?
I think I remember. Can you tell me what year is this from?
The paper is from 2021, so it's relatively recent.
Okay, yeah, maybe I remember reading something about that when it came out, but I didn't go back to it after all this work. So maybe I should. Thanks.
Okay. Yeah.
Can I ask?
I'm just trying to basically I have like an applied problem, and we formalized something like a sorting algorithm thing with bialgebraic semantics. We formalized this in ACTA, and this construction, we ended up getting a construction where you go from an inductive data type to an inductive data type, because we worked with a data type that was indexed over like a finite multiset. So anyway, like I have kind of the opposite problem to yours. I have a concrete problem. I'm trying to find the general theory that that works, and so I was wondering if this talk would help me understand it more. But I haven't managed to unify anything directly that I saw today with the things that I'm looking at.
Yeah.
So.
Yeah, but I mean the topic is definitely interesting. So do you have anything that I can read about your practical problem, or is still in the air in the Overleaf GitHub /
I do. I have my master's thesis about it. I could send it to you if you want to have like a quick look and could see if you think that something immediately springs out. That would be helpful.
Yes, please. Please, thanks.
Thanks.
And I look into that paper and write to you if I find that there is some matching somewhere. But I feel like there is. Thanks.
Thanks.
Okay, well, I think I might pause the recording or stop the recording, and we'll take further questions offline. But let's thank Greta once again for a very clear talk. Thank you.
Thank you.
Sorry, I just noticed we have a question. Let me take that back. A question from somebody without a mic working. If you'd like to type it, I could read it out. This is coming through the chat.
Or if it's too long, if you feel like it, just write an email if you think it's easier. But I will gladly answer now if you feel like writing.
Sure. So the question is, have you heard about displayed categories? They might be useful for formalizing things about fibered categories.
Yes, actually, they are. I think. Okay, I don't want to say something terribly wrong about the history, but I think they kind of arose different places and then got to very close, I say. But yes, I haven't thought of using them in this context because maybe they can give us some tools that we haven't thrown at this bunch of things yet. So yeah, I haven't thought of that. But yeah, I know of them. I just usually see them more from the one of the logic perspective. But yeah, I think it's cool. Thank you. I write that down as well.
Great. Yeah, there's a comment that in the past, these have helped people work with cloven fibrations and so on. So thanks for that suggestion.
Yeah.
Okay,
Yeah,
please.
I just wanted to say yes, because cloven fibrations are usually those where substitution works the way that you usually want to in logic and when working with types. So yeah, I think it's a great suggestion. And actually, since all our fibrations are actually split, they are in particular cloven. So it would be cool. It's a good suggestion. Thanks.
Okay. So I will stop the recording now, and we'll be back again in 2 weeks with Evan Cavallo speaking about something or other. So great.